excursions into very many things related to differential calculus. Let me add a couple of more important results that we will use very effectively towards investigating functions, solving problems. Without getting very formal about the proofs of these results, one of the things is that if there is a function y equal to fx, continuous and differentiable in an open interval a to b. There is a function y equal to fx, continuous and differentiable in an open interval a to b. And vanishing at the endpoints of the interval. That means fa equals fb equals 0. Then there must exist a point C, at least one point C in the interval. There must exist at least one point C must exist such that f dashed C is 0. Such that f dash C is 0. F dash C 0, suppose this point is referred to as A, this point is B. F dash C 0 means the tangent drawn at x equal to C will be parallel to the x-axis. F dash C equal to 0 means the tangent drawn at x equal to C will be parallel to the x-axis. Yes? F dash C 0. F dash C equal to 0 means this is parallel to AB. This is parallel to AB, right? This is what featured in the manuscript of Professor Rolle, and it's referred to as Rolle's theorem. It's referred to as Rolle's theorem. Rolle's theorem. So, if a function continuous and differentiable in an open interval a to b vanishes at the endpoints of the interval a to b, there must exist at least one point C, x equal to C, where the tangent will be parallel to the x-axis. That means f dash C would be 0. Now, more generally speaking, that means there must exist a tangent between A and B. There must exist a tangent between points A and B that is parallel to AB. That is parallel to AB. That's what it means essentially, physically speaking. Forget everything else. What it really means is if this function is continuous and differentiable in the open interval a to b, there exists a tangent parallel to the line joining the endpoints of the interval. This is what it means physically, right? However, Rolle prescribed it as vanishing at the endpoints of the interval because it need not be important for the function to vanish at the endpoints of the interval. Think of this as a rigid wire. Think of this as a rigid wire. Okay? And say there is this point where the tangent is parallel to AB. Okay? Now, I cause the rigid wire to have an upward translation. I cause the rigid wire, this is my rigid wire, and I cause it to have an upward translation. Right? That means now, if I cause it to have an upward translation, say parallel to the y-axis, then would you realize the point A and B would get raised by the same amount? Point A and B would get raised by the same amount, right? This point P will still be such that the tangent will be parallel to AB. The tangent will still be, right? This tangent, if you raise it up, will still be parallel to the line joining the endpoints of this. This is a secant. AB is a secant to this curve. And there exists a point P where the tangent will be parallel to the secant AB. This is a case where FA will still be equal to FB. FA is still equal to FB, but not equal to 0. But not equal to 0. But you still have a point P where the tangent is parallel to the line joining A and B. That means f dash C is still 0 because AB is still parallel to the x-axis. AB is still parallel to the x-axis. Strictly, Rolle's theorem is this, but will still hold good if FA and FB are equal. That means the values at the endpoints of the interval being equal, there will still be a point P where the tangent will be parallel to the x-axis. Now, not only this, realize that this is a rigid wire. Again, yes, please come in. Please come in. We rotate AB. We rotate this curve by an angle theta. We now rotate this curve by an angle theta. Right? That means AB will rotate by an angle theta, right? Now, f of A and f of B are not equal. Right? Realize f of A, this is f of A and this is f of B. They are not equal. I've rotated this very rigid curve by an angle theta. Translated, nothing changed. I still had a point P that was parallel to AB. Hey, now that point P would feature somewhere here. And this tangent will still be parallel to AB. Yes or no? This tangent will still be parallel to AB. Would you not want to believe that? I mean, suppose this tangent was also a rigid wire. And I rotated the whole thing by an angle theta. That rigid wire, which is the tangent, will still be parallel to the line joining A and B. Isn't it? Will that fact get disturbed by rotating the curve by an angle theta? Not at all. Not at all. That means this time, FA and FB not equal. FA and FB not equal. The point A has coordinates A comma FA. The point B has coordinates B comma FB. Right? What's the slope of AB? Slope of AB is y2 minus y1 by x2 minus x1. Right? So which is like a FB minus FA. Right? By B minus A. This tangent is at x equal to C. Right? What's the slope of the tangent? F dash C. That means this slope must be the same as slope of AB. That means this must be equal to F dash C. There must exist a point x equal to C where F dash C would be parallel to the line joining AB, would be parallel to the second AB. Right? That means there exists a point C for which F dash C is FB minus FA by B minus A. And obviously if FA and FB are equal, then F dash will exist a point C where F dash C becomes equal to 0. This also is only Rolle's theorem. Original Rolle's theorem, we raised it up. We got this FA and FB equal but not equal to 0. Tilted by an angle theta, I got this where there exists a point C for which F dash C is FB minus FA by B minus A. Right? Tangent parallel to the line joining the endpoints. This also should be looked upon as Rolle's theorem only, isn't it? But unfortunately not. This is looked upon as Lagrange's mean value theorem. This is looked upon as Lagrange's mean value theorem. LMVT. Mark the words. Why? Mean. Very mean of Lagrange. It was only Rolle's theorem. All that he did was rotated that very curve by an angle theta, and he said, hey, now this is my theorem, LMVT. All right. Pretty mean though. Very great. Lagrange and Rolle both were, the greatest ever. But this I thought was one case of plagiarism. Yes, this was plagiarism, I thought. And I would, if I was at the helm of affairs of the Society of Mathematicians, I would deem this also as Rolle's theorem only, instead of calling it Lagrange's mean value theorem. Mean, of course, there are many connotations to the word mean here, but one of them is the genuine mean. Okay. Nevertheless, Rolle's theorem, or modified Rolle's theorem as I would call it. No, don't be so sorry. Rolle's theorem, or modified Rolle's theorem. No, don't quote me anywhere on this. This is for local consumption. Okay, this is Lagrange's mean value theorem for your consumption. Otherwise, you go out and suggest this fellow called it modified Rolle's theorem. You know, they'll modify me. All right, so no, we'll so outside you can call it Lagrange's mean value theorem. For in my class, you can also call it modified Rolle's theorem, right? So this one theorem and its modification uh, will help us investigate functions more closely. We get an additional tool to look at various aspects of a function and its derivative. So what we are going to now do is, I'll very quickly breeze you past some of the problems. Now, one thing that I must tell you is, the challenge in applying Rolle's theorem, sometimes the function fx would be served to you on a platter. All right, they'll tell you, okay, this is the function, these are the endpoints of the interval, and you know, apply Rolle's theorem or Lagrange's mean value theorem. But there are times you would have to work backwards to obtain the function on which Rolle's theorem or Lagrange's mean value theorem would have to be applied. All right, that becomes the challenge. Not difficult, but there are times it would make you think. All right, in the problem solving session that I'm going to quickly illustrate, we will learn a few things, or at least a few ways of how to obtain the function going backwards on which Rolle's theorem or Lagrange's mean value theorem could be applied, right?